feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction video here with Mr. Gaines as we continue our work with rational functions. Today we're going to focus on graphic features of rational functions. So let's kind of use a example to take a look at what the domain of a rational function is going to be. So we've looked at domains of many different types of functions, and most of the functions that we've looked at this year have had domains of all real numbers, with polynomials and quadratics, with lines and absolute value functions. The exception to that had come with the root functions. Even root functions with an even index had a restriction on the domain because we could not have negative values inside the root. What we're going to find with rational functions is that there are going to be values that cannot exist for x, and therefore there's going to be some restrictions on the domain. So if I take a look at the function here in 2a, it says algebraically find the domain of each of the following functions and sketch an accompanying graph. So if I just take a look at the graph, and right now in our function, I'm going to assume that x could be any real number. Well, what we also know is that the denominator of x cannot be 0. We cannot have a 0 in the denominator of any fraction. So my denominator, x plus 1 in this case, cannot equal 0. So therefore, x could not be negative 1. So we know that at least negative 1 cannot be a solution for x. And so this is actually going to kind of hold true. We're going to have a rule that works for any rational expression. So given, let's say, r of x equals n of x over d of x. So n of x and d of x are real valued expressions. So it could be a integer or a polynomial. The domain for r of x will always be all real numbers except where d of x is equal to 0. So in this case, we can see the factored form of the denominator for 2a, or it would be the value negative 1 cannot be a value because that would set the denominator equal to 0, and we could not divide by the denominator. So we would say that the domain for this function would be all real numbers not equal to negative 1. You could also write this as x is less than negative 1 and x is greater than negative 1. In most cases, you'll see it written as all real numbers except for the values that would not be or would give you a 0 in the denominator. Now let's go ahead and take a look at the accompanying graph for this. So I've already put this graph or this function into my calculator. Under y equals, you can type that function in, but I'm going to go ahead and look at the graph. So what we're going to see here is we're going to see kind of a different kind of graph than what we've seen frequently in Algebra 2. So if we want to sketch a graph for this, what we have is a function that's going to cover all real numbers except for negative 1. At negative 1 in this case, negative 1 would be considered a vertical asymptote. You may have heard the word asymptote previous in other classes. Asymptote is essentially a value or a location on a graph that the graph will not cross. The graph will approach this value as x goes to this value, y will either go to negative infinity or positive infinity would be the official definition. You'll learn more about that in pre-calculus. Right now, we just kind of need to identify what that value is. So what we would have here is where x is equal to negative 1. I'll draw this in as a dashed line. And we'll say this is, again, x equals negative 1. This would be a function that, or a location on the graph that the graph cannot intersect. So the graph would look something like this. It would approach going up from the right side of the graph. And actually there's a horizontal asymptote, which we'll speak about more as we progress through these notes. So it'll approach the x-axis but never cross the x-axis. So we can see the same thing down here over the left where it's going to approach x equals -1, but this time going to -infinity on the y-axis, and then it'll approach the x-axis. So if we were to take a look at the table, what you'd find is you'd find values for any number except for -1. And we'd also see that as I go further and further to the right, the values for y get closer and closer to 0, but they never reach 0. So this is kind of the process of what's occurring at an asymptote. Now let's take a look at problem number 2. Problem number 2 may be a little bit more difficult to find the domain. Really here, if we can factor the denominator, we can identify the domain a little bit easier. Remember, the domain is all real numbers except for where the denominator is equal to 0. So if I factor this denominator, it's a quadratic trinomial, so it's going to factor into two binomials. 2x and x may be my initial terms in each binomial. We may recognize that one of these terms, one of the second terms is going to be positive. One of them is going to be negative because it has to multiply together to give us -3. The only factors of 3 are 3 and 1. In this case, we'd have x plus 3 and 2x minus 1 as our two factors. This, through distribution, would give us the 5x in the middle term. So then what we can see here is once we have the factors, the domain is going to be any real number that would set either of these factors equal to 0. So if I put in a number here in, let's say, -3, we could see that that would be -3. If I could put in a -3 here, the factor on the right would be 0, and it would times the factor on the left, multiply to the factor on the left, creating a 0 in the denominator. So essentially what we can do is we can say that 2x minus 1 cannot equal 0, and x plus 3 cannot equal 0. And then you'd go through the steps, so therefore the domain is all real numbers except for +1/2 and -3, the two numbers that would set this equation equal, or sorry, set the denominator, would create a 0 in the denominator. Now let's take a look at this graph. Again, I've typed this into my calculator already. You could type it in as well if you want to get a picture of that. And this graph is going to look a little bit different. What we see here is we see some similar type looking curves with that we saw previous in 2A. We see that curve in the bottom left and the top right look the same, but then there's another curve that's going to come in between them. In this case, what we have is we have two vertical asymptotes. So if I sketch out my graph here, both of these values that x cannot equal are going to end up being vertical asymptotes. So we have one of them at +1/2. So again, I'll draw this in as a dashed line. So this is x equals 1/2. And we have another one at x equals -3. So now my curve is going to look something like this. So we don't have to draw the graph in exactly as it appears. We don't have to be perfect with our drawings here, but we want a sketch that looks something like what we see in the calculator. And again, we see two asymptotes as the graph approaches those values for x that are not part of the domain. So a rule for asymptotes, vertical asymptotes, anytime a 0, or for any value where a 0 would be part of the denominator, or any 0 of the denominator that is also not a 0 of the numerator, will be a vertical asymptote. So in both cases where we found the values that x could not be, those were restrictions on the domain, but these would not give a 0 in the numerator, or a 0 for the entire function, and so they would not be, or sorry, they would be vertical asymptotes. Now let's take a look at C. C is a little bit different. So if I factor C here, you're going to notice for the denominator that we're going to factor this into x minus 6 and x plus 1. Now what you may notice here that we haven't seen up to this point is you could essentially simplify h of x as 1 over x minus 6. However, the restriction of the domain from x plus 1 still exists. So x could not be 6, and x cannot be negative 1. Even though the factor from the numerator and the denominator can be simplified, that value that is a restriction on the domain still needs to be accounted for. So in this case, x could equal all real numbers except for negative 1 and 6. Now, if we take a look at the graph here, the first graph had one asymptote. The second graph had two asymptotes. We may look at this and see that there are two restrictions on the domain, so we may assume that there's going to be two asymptotes. Let's go ahead and take a look at the graph. So as I graph the vertical asymptotes here, or as I graph this function, we can actually see that there's only one asymptote. The asymptote is at x equals 6. So let's go ahead and let's sketch this. So again, this one kind of threw us for a little bit of a loop here, something that we didn't quite expect to happen. We thought that because maybe there was two restrictions on the domain, like the previous one, there'd be two asymptotes. But in this case, there's only one asymptote. Now, what may occur at x equals negative 1? Well, let's go ahead and take a look at the table. X equals negative 1 still does not show up as a value on the graph. So x equals 6 shows up as error because it's not part of the domain. X equals 1 shows up as error because it's not part of the domain. However, we don't see an asymptote there. What we get in this type of graph is what we call a hole, often referred to as a hole. A hole in the graph occurs when we have a factor of the numerator that matches a factor of the denominator. For essentially any zero of the denominator, which cannot be part of the domain, is also a zero of the numerator. So there are two types of restrictions on the domain. There are vertical asymptotes, when it is a zero of the denominator but not the numerator. And there are holes when you have a zero of the numerator and the denominator. Let's go ahead and take a look at two more problems. And in this case, we're going to go ahead and identify what type of restrictions on the domain we expect to see before we graph. So if I take a look at problem 2D, our directions are still the same. What I'm going to do here is I'm going to factor the numerator and the denominator. So the numerator is going to factor into x minus 2 times x minus 2, or x minus 2 squared. I want to make sure that I factor the numerator and the denominator to determine if I'm going to have a hole or an asymptote. So that, or in order to do so, I need to see both of my factors. So when I simplify this, sorry, I made a mistake there. The denominator should be x minus 3 times x plus 1. When I factor this, I can see that there are two restrictions in the domain. There are two cases that x cannot equal. So I cannot have a 0 in the denominator, so neither of these factors can equal 0, so x cannot equal 3, and x cannot equal negative 1. In this case, because neither of those are a restriction, or sorry, neither of those are a 0 of the denominator, we don't have any factors that match in the numerator and the denominator, both of these are going to create vertical asymptotes. So the domain would be all real numbers except for negative 1 and 3, and both of these would be vertical asymptotes. Now let's take a look at that graph. Again, I've preloaded the graph into my calculator. If you need to pause and type yours in, you can do so. And what we're going to see here, I'm not going to sketch the graph just to save you guys a little bit of time. But what we're going to see here is we do have two vertical asymptotes, one at negative 3 and one at positive 3. Now what we see in the curve here with the graph in between is, in this case, the graph changes direction in between the two asymptotes. So previously when we saw two asymptotes, the graph went from infinity to negative infinity on the y-axis. In this case, it's going to turn around. And in pre-calculus, you'll learn more about why these things occur. Really, what we're looking at finding is restrictions on the domain, what type they are, and then we'll leave the graphing to the graphing calculator. So if you want to sketch that graph, you can, but the real goal here is to find the domain and identify that both of these are going to be vertical asymptotes. Now let's go ahead and take a look at 2e. In this case, we want to factor if we can. So identifying any zero of the numerator and zeros of the denominator. So our numerator cannot be factored, at least cannot be factored using real numbers, and that's all we're working for right now is because we're thinking about these on the graph. The denominator could be factored. It would be factored into x plus 1 times x plus 1, which is x plus 1 squared. So in this case, we only have one value that x cannot be, and that would be negative 1. So the domain would be all real numbers except for negative 1. As that 0 of the denominator, negative 1, is not a 0 of the numerator, this would be a vertical asymptote. Now, if we take a look at the graph of this vertical asymptote, or the graph of this function, we can see that, again, there's only one asymptote, and it is at negative 1. In this case, we can see that the curves are on the same side of the y-axis. So previous to this example, we had seen one asymptote. The curves were on different sides of the y-axis, which was the horizontal asymptote. In this case, the curves are on the same side. Okay, again, you'll learn more about why that happens in pre-calculus. We just want to identify that the vertical asymptote is there, and if we need to graph, we'll go to the graphing calculator. This looks like a good place for us to stop for right now. So what we have discussed in the second part is the domain of rational functions. The domain for all rational functions that we will see in Algebra 2, again, is going to be all real numbers except for any location or any value that's going to give you a 0 in the denominator. In one case, when that is a 0 only in the denominator, it will create a vertical asymptote. When it is 0 in the denominator and the numerator, it will create a hole. As always, thank you guys for tuning in, and we'll see you soon.